So let's begin then. Welcome to this talk about targeted static analysis for OCaml C Stubs. I also called it eliminating gremlins from code because gremlins are about these unpredictable bugs, and data races are always unpredictable and hard to debug. So this tool I developed as soon as I found some bugs in some C bindings that I've written myself, and I adapted it so it becomes a more generally useful tool that can detect bugs in OCaml C bindings, not specifically just on the project that I'm working on. I'm hoping that this will be useful in general as well. So I'm working on the Zapi project at Zen Server. It's an open source project with a large part written in OCaml, but it needs to interact with the system. So it has a lot of C bindings. So one perhaps surprising realization from, at least for a C programmer, is that when you combine OCaml with C, you get something that is more unsafe than C. So how is that possible? So we all know that if you use OCaml code and you don't use any of the unsafe features, then it's a memory safe language and it has all these nice properties. It's type checked and you don't have use after freeze and your program doesn't crash. If you use C, you don't have those protections, but you still have some type checking. And there is no garbage collector on the C side usually. Now, when you combine OCaml with C, you lose some of these properties because the OCaml compiler is not aware of how you have implemented your C code. It's very easy to make a mistake and call a function with 4 parameters instead of 5, and you'll only detect the problem at runtime. There is also the problem that now the OCaml compiler can move some values at runtime, and you have to be very careful in how you write your C code. You have to follow very closely the manual, which describes how to write safe and correct C bindings. You might think that OCaml C types would be the solution for this, and indeed it does bring some type safety back. So you have type safety at the level of function calls, but it trades off some other aspects. I'll show some examples later about tracking lifetimes, that you now need to track lifetimes of values on the OCaml side. So we still need a solution that works with pure handwritten C code. So what would that be? There are too many constraints to keep in someone's head. You need a compiler to do these sort of checks. Before developing a tool, let's look at some examples of what bugs I've actually encountered. So this is one particular issue. So there was this piece of code with a primitive called domain assign device. It was committed into this entry. A couple of years later, someone changed the C code. They helpfully updated the C stub to match the C code and pass in an additional flag. They forgot to update the OCaml part. And while as C developers, they're not aware of how the FFI works, and they would have thought that some compiler somewhere would have given them an error. But it hasn't, because there is no checking in between those. So in this case, using OCaml C types would have been a solution, but that's an easier solution, that's a more common solution for this kind of problem in C, is to have a header file, right? So the header file will tell you exactly what prototype your function should have. So, okay, let's try writing some code to do that. So we can parse an ML file. I'm reusing the OCaml compiler libs here. We can find all the primitive declarations, and we can generate some header files, and that can be done in surprisingly small amount of code. So it's like less than 50 lines of source codes to do that based on the parse tree. If you want a bit more accuracy, to also deal with unboxed and untagged, then you need to go to the type tree, but that's still quite a small amount of code. For now, these are separate tools. They're available on OPAM. In the future, if there's interest, I might propose integrating this into the OCaml compiler itself. But first, let's develop it separately see how well it works. There's also some test code with it. So this is written using Dune's crem style test. Example taken from the manual on how to write some code, and it generates this header. And now this header can be used with the C compiler to check the number of arguments match. So this isn't any fancy kind of static analysis, yes, but it is a build time analysis. And let's look at another example where we have a data race, which was actually introduced when porting some code to OCaml 5. And you probably cannot see the bug just from looking at this patch. So if this is the patch you receive to review, you would need some more context. You would need to look at the surrounding code, like what's age and how are all these values used. So the part that's actually not visible in the diff is how the code is used. So in this case, the runtime lock is released, then you use this macro, and then you reacquire the runtime lock. And that's not safe to do because you are dereferencing this value, which is an OCaml value, while you have released the runtime lock. And that's something the manual tells you not to do as well. And it's in general an unsafe thing to do because at that point, the garbage collector may run, it can move your value, and you may end up dereferencing a stale pointer. Now, normal kind of static analyzers that you can run on C are not aware about all of these special rules that your OCaml GC imposes, so they are not able to help you with that. But I'll show you a small tool that I developed that can generate some annotations that allow an existing static analyzer to actually be able to tell you about exactly this kind of problem. There are some more difficult to understand problems that you can encounter as fails. So you might think, okay, the rule is you cannot have any OCaml value dereferences inside the block, right? And then everything should be safe. That's not entirely true because this interface appears to be C pointer, right? It's a struct mmap interface. But in reality, that's actually an OCaml abstract tag, right? It points inside an OCaml value. So that's not safe to dereference. So you have to be careful even with these kind of code. So indirectly, anything that points inside an OCaml value is not safe to dereference when the runtime lock is released. There are some other complications that I left as feature work, so I'm not dealing with callbacks now. And actually, before OCaml 5, it is very difficult to write callbacks correctly when you release the runtime lock because you need to know, do all the code paths release the runtime lock, or do all the code paths do not release the runtime lock? Because your callback will need to call back into OCaml code, and it will need to know whether to acquire the runtime lock or not. But it doesn't know in what state the runtime lock is. So that's actually quite tricky, and there was actually some very old code in Zen that didn't end up being used, but when run with the free on exit feature of OCaml, it's segfaulted, and it's because of this mismatch. It doesn't know that some code paths release the runtime lock, some others do not, and then it cannot use the callback safely. OCaml 5 improves this situation. There is a OCaml state OPT macro that you can check in what state you are. But actually statically verifying this would be a lot more complicated than what my tool currently does. So I mentioned briefly that OCaml C types might be a solution for this. There's a link to an issue, GitHub issue at the end of the talk with some more details. But even with OCaml C types, you have to be very careful how you use it, and you have to manage the lifetime of your values very carefully, because in this example, this f function ends up being an external function from C types, and you allocate some value on the OCaml heap, and you pass it. But then if you don't reference this value anymore, the OCaml GC can move it. And the C code just receives a pointer to it, so there isn't anything holding it alive anymore. So you have to manually keep it alive using opaque identity across calls. And this can become quite tedious to spot these kind of errors. And you would still need some kind of static analyzer, this time on the OCaml side, to detect these problems. Now, don't get me wrong, C types is great. We use it a lot in Zen server. but you need to be aware of these limitations. So the main problem here is lack of tooling to do these kinds of checks, right? So C has a lot of static analyzers, runtime instrumentation frameworks, but it doesn't interact well with the OCaml side. So I've written these two small tools. It's called link-C Stubs genmain and genrep, which synthesizes some functions to help static analysis. So genmain generates a main function that shows you how everything is invoked, and then you have genrep, which generates a small wrapper that asserts various properties about the code. And this is actually some new feature that I added after I submitted the paper, so you won't find the details of this in the paper. It's still all very, very experimental. But just if you want to see how the generated wrapper looks like, so you have a C stub that takes an input channel, an integer, and returns a unit, and it generates this assertion that this has to be a block, this has to be a long, this has to be a long with a value 0.
Excuse me,
and
Edwin.
So on and so forth.
Edwin,
yes?
Can you please increase the font size?
Yes, we can do that. Is this better?
Even larger would be nice.
Okay. Is this
yeah,
good?
this is great. This is great. Thanks.
Okay. So we have the int channel, then you have the integer, and then you have the unit. And of course, you can have more complicated types as well. Like there is a test here that it takes 2 arguments. Like it also takes a closure, right? And it has to be a closure tag and a non-null code pointer. It has to be a character. Then you can also validate the range and so on. We only support very simple shapes, like basically your OCaml primitive types, tuples and arrays. Records are still in the works, and more variants and polymorphic data types. The tool will just ignore them, so they won't generate assertions. It will still work correctly. So this would be the wrapper. I can also show you how the main function looks like. So this would be the main function. We create 2 threads specifically, so the main thread plus another one, to tell the static analyzer, to show the static analyzer that these functions can be called from multiple threads. And then basically there is this function which invokes all the C stubs, and it invokes them based on this non-deterministic choice. So it's basically a random number. That's needed because otherwise the static analyzer finds a bug in one function, then it assumes the program crashed at that point and doesn't analyze the other C stubs, right? So we need to tell it that it can invoke either this one or that one or that one. So it actually tests all of your C stubs when you use the main function as your entry point. And it also tells it the state of the runtime lock, right? So we simulate the runtime lock with a pthread mutex. And you can see these wrapper functions. They generate basically some random values to give it. So it's not something you could execute because these are random values, and if you actually executed the program would crash. But from a static analyzer point of view, it's useful because then you would have the assertions generated by the wrapper, and it would know what values it has to give to the function and what values to expect. So these are code that looks like C, but essentially it's a C model of how these C stubs could be invoked by the OCaml code, which the C static analyzer cannot inspect. And now we can give all these files to a static analyzer. So in this case, I used, I'll skip over a few slides here. So I use this framework called Goblint, which is an analysis written in OCaml. It's built on top of SEAL, which is quite an old OCaml static analysis framework for C. And Goblint is tuned specifically for data race detection. And it has a lot of reasoning code already about locks. Now, we can't use Goblint as is. We need to teach it about the runtime lock. But actually, it requires very little amount of code to teach it about the runtime lock. I'll show you some results of what I achieved, and then if there's still a little bit of time, then I can show an example. So the tool outputs, of course, it has a CLI, it has a web UI, it has a VS Code plugin. So that's all existing tooling in the ecosystem that I'm using. So this is an example, right? So it's a GitHub CI that you run, and it tells you, yes, the domain lock must be held when referencing the OCaml value. And I specifically configured the static analyzer to show just these warnings, because otherwise it would show a lot of warnings about maybe the referencing null and things that come from the imprecision of the analysis. But the data race one, it shows it only when it's confident that it's actually an error. This is an internal UI that the Goblint framework provides. It's the same kind of error, but you can inspect the static analysis state. You can see the lattice there. It shows the mutex, that there's a mutex, the OCaml runtime lock that is being, what state the mutex is at that time. So there's a lot of future work here that we can do. So I used one static analysis framework, but there is some kind of tooling around it. I try to keep it generic. That's why you see that there's like 4 or 5 tools instead of a single one, because each one does a small piece that's useful on its own and could be reused with other tooling in the C ecosystem. Like in the future, we might also do some runtime checking with a tool like CLI, for example. So the tools are going to be published on OPAM soon. So the C header generator, the link C Stubs RFC, that's already on OPAM. The actual static analyzer that's being packaged now. I'm working through some failures the CI has found, but it will hopefully be there. It's already on GitHub. You can see it here on my slides being referenced. I can also put some links to the slides in the chat. And then very briefly, while people are thinking about questions, I can show just one example of how this is actually being implemented. So this is actually the core of the implementation. And then it reuses a lot of functionality that already exists inside Goblint, except this domain lock must be protected by, and then in domain lock, domain lock is implemented here as well. It's not a lot of code. Essentially, it's a wrapper around what already exists in Goblint. So this would be must be protected by. We ask Goblint the state that we're interested in. We model this runtime lock with a single mutex in this case. So this models OCaml 4 at this moment, but it's already quite useful at catching problems for OCaml 5 as well. And then we assert that it must be held, and if it's not, then we show this error. I saw a chat message about a question on the GitHub CI. So there is actually a link here at the end of my talk. I think, yes, this Sarif support for code scanning. So all you need to do is generate this Sarif XML, which Goblint will do for you. You can also use other tools to generate it, output it in your GitHub action, upload it, and then GitHub will do the rest. It will show the warning at exactly the line that the problem happens at. So that's tooling that I was able to reuse. So if people have questions, I'd be happy to answer them.
All right. Thank you, Edwin. Is there any question in the audience?
Sorry, can you repeat?
I was asking if there was any question in the audience. There is none, but I have one. So have you actually found bugs in widely deployed libraries in OCaml that were using OCaml C types?
So OCaml C types, I found the bug in the Zapi project, which is the project that I'm working on. There was one particular problem with string lifetime handling, and we never really got to the bottom of how to make that work correctly. I'll have to try again with the latest version of C types if the problem is still there. and then open another issue. It's a bit tricky to reproduce, but it's the kind of bug that you think you have fixed, and then a month later in your CI, the program crashes once a month. In all fairness, it might have been a bug that has been fixed, as that was like 4 years ago that it happened.
Okay, thanks. Another question?
So first, thanks. That's cool. Otherwise, do you have integration with Dune to just plug that in a project?
So I have some integration that generates just to make it easier, because you have to find the CMT files that I'm working on. You have to find C files. It's just to make it easier to invoke, because it can become quite tedious to write it by hand, right? So you can see it. You have to write quite a few rules. You have to take the CMT file, generate the model, then run the other tool, then run the other tool. You could write all of these rules by hand. You could also use this tool that outputs Dune rules for you that you can put in your project to use. This part is still very experimental and under development. It works on this small example that I have here, and I'll work on getting it ready to be used by other projects. But yeah, this tool works with Dune. The other tool, the GC Stubs arity, that works with just make files as well. And there isn't any dependency on Dune specifically. So if you have another build system, you can use the same kind of rules in that build system as well. It will work just as well. And Goblint itself relies on this compile commands.json, so that tells you how to, all the flags you have to use to compile your C code.
I have another question if there's no more in the audience. How practical is it? I mean, can you give us a, can you tell us how much time it takes for Goblins to analyze one of the stubs that you have been studying?
So on Zapier and the Zen project, I think the CI runs in about 10 minutes. So specifically, the step to analyze this runs in about 10 minutes. And the way I do it, I analyze each C file separately. So you could even maybe gain some speed ups by parallelizing it. On the Zen project, it takes a little bit more because it has very big files, and I actually have to tune Goblin to not do so precise analysis. Otherwise, it runs for loses a lot of memory, runs for a long time. But once I tuned it and I shipped this tuning file as a JSON, then yeah, in a couple of minutes it terminates. Obviously, if you want more precision, you can tune Goblin to do some more precise analysis. But for what I did here, that seems to be enough. I haven't tried on any projects that are a lot bigger. Yeah.
Okay, thanks. Thank you, Edwin. That was the last talk of this session.